Good morning, everyone, and welcome to the Trusted CI webinar for September 22nd, 2025. I'm your host, Jeanette Dopheide. Trusted CI is the NSF Cybersecurity Center of Excellence, and these webinars are part of its mission to deliver high-quality, actionable guidance regarding cybersecurity to the NSF community. More information about Trusted CI can be found at trustedci.org. Today's topic is No Harness, No Problem, Extending Fuzzing's Reach via Oracle-Guided Harness Generation. Our presenter is Dr. Stefan Nagy, who is an associate professor at the Kahlert School of Computing at the University of Utah, where he directs the Futures Lab. His work lies at the intersection of software engineering, computer systems, and security with a focus on making automating vetting of software and systems more effective and efficient, irrespective of kernel, architecture, and source code. Before we begin, I have a few things to note. First, this presentation is being recorded, and second, participants are welcome to type questions in the chat during the presentation. And with that, I will hand things off to Stefan. Stefan, welcome.
Thank you so much. I should clarify, assistant professor. I'm not there yet at the bar of tenure. So, all right. Well, thank you so much. Yeah, it's an honor to be here, and I'm really excited to talk about some of our work on extending, the breadth of fuzzing across as much of today's software as we can. All right. And so, if there's any questions, feel free to, I guess, type in the chat or interrupt me. I can't see your hand raise emojis over Zoom, so
Yeah, I'll be watching the chat for you.
beautiful. All righty, cool. Let's get started. So a bit about me. So my name is Stefan Nagy. So I'm an assistant professor here at the University of Utah in the Kahlert School of Computing. I'm the co-founder and co-director of the Utah Software Security Group. Before joining Utah, so I did my PhD at Virginia Tech, and then right before that, I was doing my bachelor's at UIUC. So I know there's some UIUC folks here. So really great to have some alumni here. So at Utah, I lead the Futures Lab, which stands for Future Tech for Usable, Reliable, and Efficient Security of Software and Systems. We work with the NSF and various elements of the DoD, primarily the Air Force Materiel Command, on trying to improve the reach of fuzzing, from all different aspects, whether it's, domain-specific testing to just trying to eke out a few more, percentage points of coverage across, mainstream ubiquitous pieces of code that, need thorough vetting. And then my URL is just futures.cs.utah.edu. One of the, joys of being a fuzzing researcher is that we get to find bugs. This is the ultimate, sort of really fun thing that we get to do that my students and I, try to work on, and we like to report bugs and disclose them and work with developers to get them fixed. I think we're one of the only research groups that I know of that actually put up a bug tracker to kind of list all of the bugs that we find across our various projects. Many of the bugs that I'll discuss here are housed on this bug tracker, which is just futures.cs.utah.edu/bugs. Is there a question in chat? Can people hear me?
No, we're good. Thank you.
Okay.
Oh, it says the URL. Oh, that's my fault. I'll fix that. Apologies.
Okay.
Please continue.
Sure. So most of the work that we do is, like I said, trying to improve the reach of automated bug discovery. And so a lot of my early work focused on this problem of how can we, improve security vetting of closed source code, everything from firmware to proprietary intellectual property, all these different things. We had a number of successful papers there improving, the throughput of testing, especially in these really, really opaque, kind of hostile use cases. From there, much of the work that I'm currently pursuing is on domain-specific testing, everything from, how do we improve software development tools by feeding them test cases and seeing where they fail. This, of course, extends across compilers, decompilers, transpilers, as well as other kind of interesting classes of bugs that, I think have not been getting a lot of attention from, my community at large, and this is a lot of work we're doing on graphical user interfaces. From here, the work that I'll primarily talk about today is on this problem of how do we, try to improve the vetting of ubiquitous code. This is little pieces of software that are everywhere in the software stack, from our web browsers to our operating systems, everything in between. And so how do we, find the code that we are not successfully testing, and then how do we, try to find the bugs that may be lurking in between. All right, and so I'll talk about three core projects here within this line of work. So the first was just published at the International Conference on Software Engineering this past May, I believe. Yeah, May. And then we have two other projects, one under submission right now called Snake Charmer, which is sort of an extension of this work to Python, and then a new collaboration with some folks at Google on sort of hybrid automatic harness generation techniques. All right, so I'll first talk about a technique that we came up with that is kind of the foundation of all our work in this space called Oracle guided harness generation. So as many folks here probably know, fuzzing is by far the most popular, most deployed, and also most successful technique at uncovering software bugs. And so at a very high level, I know Barton Miller, I think, is in attendance, and he's sort of the inventor of fuzzing. But at a very high level, fuzzing is kind of three core steps. The first is to just generate as many inputs as you can, feed them to the program or a library or whatever kind of piece of software you've managed to hook up testing to, and just see what happens. Does it cause the program to enter an infinite loop and time out? Does it crash the program, or does it just do nothing at all? Or maybe there's some domain specific sort of behavioral oracles you can sprinkle in between to flag other kinds of interesting behavior. And then for most fuzzing today, which is what we call code coverage guided, the idea here is to sort of find the test cases that eke out a little bit more percentage of lines of code or basic blocks or whatever your metric is of progress, keep those, and then just mutate those over and over again with the goal of expanding the breadth of this search over time. And so, unsurprisingly, I mean, fuzzing has found so many bugs across all these different pieces of software that we take for granted, everything from firmware to compilers, IoT devices, web browsers, operating systems, all kinds of stuff. I mean, we're talking like tens of thousands, potentially even more hundreds of thousands of bugs across the entire, sort of software ecosystem. Now, for fuzzing today to actually work, you have to, as I said, hook up the software to your fuzzer. And the most common approach of doing this is something called harnessing, right? Specifically for open source libraries. And so at a very high level, harnesses, and I'll use this term throughout the duration of my talk, these are just simple sort of wrapper programs that are designed to call a library under test and instantiate it in the correct way, and then feed the fuzzer generated data to the API functions that we are trying to vet. So here is a simple harness of the GEOS library, which is a pretty well-known scientific computing library for all kinds of sort of geosciences applications, things like that. And as you see here, there's many different components, and they all serve a purpose, right? So we have in the beginning, we have to first make our call to the initialization function that libgeos provides us. So every time you are using libgeos functions, you have to call this this initialization routine, or else the library will just not work correctly. From there, we see kind of the initial stages of how we are passing in fuzzer generated data. In this example here, it's just simply in the data buffer. In some harnesses, there also is like a corresponding size, which is just, kind of the delimiter of this is how many bytes we're reading from that buffer at this given time. And then from there, we are setting up library sort of specific objects. In this case, GEOS has these geometry objects. And then we want to now perform some kinds of operations on these to see where these functions that take in these library specific objects may have bugs themselves. We call these functions data processors in our work. Now, the biggest problem in all of fuzzing, right? There's been so much work on how do we improve coverage performance? How do we maybe improve test case generation, all these different things. My perspective on fuzzing is the biggest problem is actually fuzzing the code to begin with. And in the context of these, large initiatives of testing these, billions, not billions, but these dozens upon dozens of libraries that we rely on, there's so much code that is just not being covered. So shown over here on the right is a screen grab from OSS Fuzz Introspector, which is Google's sort of kind of synchronizing tracking engine behind their massive OSS Fuzz project, which, to kind of sum it up, is like they have football field sized server rooms that they just devote at fuzzing these really, really popular libraries like XML, libjpeg, libpng, all these different things, right? As you see, we are still very, very far off from covering so much of the code within these critical pieces of software. And so because this code is just not being harnessed, meaning there are not these harnesses, these wrapper applications that actually correctly call so much of this library functionality, that code just remains outside of the reach of fuzzing. And this is despite there being, multiple CPU decades worth of fuzzing having been applied to these pieces of software. Now, a lot of the motivation for our work in this space of scientific software is this observation that there's not a lot of harnessing taking place in scientific software vetting. And so this is kind of a survey from our grant proposal on this. Jack Davidson from UVA and I we have this proposal from CICI on improving security vetting of scientific software libraries. And yeah, this is a huge, kind of bottleneck here. So even the ones that do have some harnesses like SciPy or HDF5, in many cases, those are very, very subpar. They're only calling very, limited portions of the library under test, or they're potentially doing so incorrectly, or, just leaving lots and lots of code on the table for attackers to exploit in the real world. So in examining how we can solve this problem, so we spent a lot of time looking at available techniques for automatically generating these harnesses, because of course, for most fuzzing, this effort of generating these harnesses is largely a manual effort. And until we can fully automate that, we're kind of still really, far behind in trying to thoroughly vet these code bases. So, the idea behind a lot of this body of work is to find ways to piece together these API, function call sequences and then correctly feed fuzzer generated data to exercise their code. And so for about the first few years of this line of work, most techniques were basically trying to look at all the available reference code. This could be unit tests. It could be built-in, developer provided applications that come shipped with the library. It could be, potentially looking at how that library's functions are used across other libraries, other applications, other third-party, code bases, things like that. And I mean, unsurprisingly, if you have examples of this function that you're trying to fuzz already being called, already being instantiated, and all the data flows and everything being passed to it correctly, this is pretty fast. All you have to do is do some minor kind of tweaks to then make it consume arbitrary fuzzer generated data. Now, the disadvantage here, and everyone that is looking at unit testing probably recognizes this problem all too well, is that so much of the code that is already being called, there's so little of it with respect to the overall functionality of these libraries. And so relying purely on unit tests or built-in applications really only gets you a small kind of fraction of code coverage versus what you'd want to test across the entire library. Now, if you can go through the trouble of building a kind of really, really precise specification of the library, all its functions, all the data types, the return types, all these different things, and this is what this work called GraphFuzz is entirely doing. You have the benefit of being able to now stitch together different API call sequences automatically with really, really high semantic validity, because you have all this kind of, all these constraints in front of you of how these API calls are meant to be sort of exercised together. But again, this is still really a manual effort. There's been no automated tooling at, piecing together these specifications in a fully kind of human agnostic way. And so it's still really, really unscalable. Now, more recently, there's been this shifting perspective of, well, then why don't we just try to kind of randomly mutate these API call sequences as we are trying to fuzz them. And so in doing this, you're no longer relying on specifications or these kind of low coverage code, reference code examples. And you can now cover a whole lot more code, a whole lot more API call sequences. But the problem is these approaches largely rely on, kind of very limited sort of restrictions of how you can use the API functions. And so they end up with many, many false positives purely from breaking the kind of semantics of the library. And these are some of the examples that we've seen in our own efforts of trying to use these approaches to test scientific software libraries like libgeos, HDF5, all these different things. And so even though, like I said, they're doing away with this requirement of specifications or reference code, they often end up breaking API semantics from missing initialization routines that must be called for that library to be exercised correctly. missing checks on API return data that would be used to then exit the harness in the event of kind of corrupted state, or even making erroneous call sequences, like for example, in this case, kind of successive deallocation routines, on the same objects, which of course lead to, all kinds of false positive errors there. So, and looking at these challenges, our kind of motivation here was how can we actually generate harnesses correctly without having to go back to relying on handwritten specifications or low coverage reference code examples. And so we took a lot of inspiration. I teach a class on fuzzing, and I get a lot of joy out of seeing my students, pick an arbitrary piece of software. That's kind of the course project is like you pick something, you try to figure out how to harness it and just start spewing test cases at it. And then you see what happens, report bugs, all these awesome things. And we learned a lot in observing how people actually perform harnessing by hand. And there's sort of three fundamental steps that have to, go in sequence before we say, okay, this harness appears good to go. We can now initiate fuzzing for it and find bugs and all these awesome things. And so the first one is, of course, okay, you come up with, a candidate sequence of API function calls, and then you have to now compile it, right? And if compilation fails, you've broken the syntax in some way. If you have warnings turned on, you can probably get more fine-grained information. But in any case, if you can't compile your candidate harness, you got to go back, start over, make modifications, and then continue. If you do get it to compile, now you would do some limited sort of testing, right? Maybe you take some example test cases for the library that you want to fuzz. For example, for libjpeg, you have the whole internet of JPEG files you can scrape, and maybe you take a subset of those, you run those on your harness, and if the harness crashes on these sort of benign test cases, that's a pretty good sign that something is not going correctly in how you are setting up the API state, or maybe you're missing initialization routines or doing these other kinds of semantic errors. And if that also works, then you would, of course, start looking at, okay, on these limited set of test cases, or perhaps in a, short smoke test fuzzing run, am I actually like getting coverage over time? There's always this problem in fuzzing of like not calling interesting functionality, or even perhaps, calling interesting functionality in an incorrect way, which leads to plateauing code coverage, which means your harness is not actually, doing anything interesting, not going to find any bugs. And so at each of these steps, we can think of these as sort of oracles. And if any of them fail, this prompts us to then go back and refine our harnesses before continuing on to, trying to pass all these three steps in order. And so in looking at how folks harness by hand, we kind of thought there's a lot of advantage to this sort of oracle guided approach, right? If you want to make sure that every single candidate API sequence must compile, execute without any error, and then of course obtain more code coverage on a limited set of test cases, we can kind of use these as sort of guardrails to then generate harnesses automatically. And so taking inspiration from how fuzzing works, right? If you think about gray box fuzzing, you're throwing lots of test cases at a program, and eventually just by the oracle of, hey, I'm trying to exercise new behavior, you eventually get deeper and deeper, more and more sort of well-formed test cases as fuzzing continues. And we kind of took this idea and merged it with these three oracles to begin stitching together, kind of like you would through fuzzing, begin stitching together candidate API call sequences, and then validating each using compilation, execution, and coverage as our as our central guiding oracle. Excuse me. Now, unlike fuzzing, where you don't really necessarily care about structure, obviously in some cases for really highly structured input formats, structure matters a lot, or else you're not going to get anywhere in testing. For most fuzzing, you're just throwing bytes at the wall and seeing what sticks, right? In our case with harnessing, you have to make some sort of strategic decisions about how you are generating these API call sequences. And so in looking at, this kind of big survey of all of the C libraries that are currently being fuzzed on Google's, massive OSS fuzz initiative, you can see there are sort of semantics about the purposes that all of these functions serve, right? So initialization functions, again, if a library has one, not all of them do, but if they have one, you probably ought to call that early in your harness, right? And then from there, setting up the correct, data flow to then pass in fuzzer generated data into the kind of initial entry points of the library to then begin calling other processors of those returned objects. And then, of course, along the way, maybe you need to set up some API-specific resolution routines. We call these auxiliary functions. These are other kind of objects, like in the case of libgeos, you have to have a reader object that is created specifically through that function called reader_create. And so with these guidelines, we want to generate harnesses automatically that follow these common case API semantic usage patterns. And so our first step, given an arbitrary library, is to pre-process its header files and kind of perform this function classification to say, okay, this looks like an initialization function. This looks like a entry point for fuzzer data. This looks like a processor that would then perform operations on fuzzer return entry point return data and all these other things in between. And of course, it's C, so we get all the benefit of type information, function definitions, type defs, macros, enums, all these things. We pull this all together as our kind of starting artifacts, and then begin, mutating API call sequences and mutating the arguments that we set up every single API call with. And along the way, every single time, we validate each mutation through our guiding oracles, right? Does it compile? And if it compiles, does it execute without crashing on a limited set of 5 or 6 test cases for that library? And if that all goes well, are we actually seeing sort of input dependent logic being exercised that would then give us an indication that this is actually a harness you'd want to fuzz, and deploy and test and hopefully find bugs with, right? And if any of those fail, we sort of wipe this off, go back, and then begin trying to mutate again and seeing what happens, and over time gradually converging on correct thorough harnesses. And then after all this, just like in normal fuzzing, you would then minimize your corpus. In this case, our corpus that we emit is just a whole bunch of possible harnesses that we validated as being likely to work without error. And we would then do some coverage minimization, give that final pool of minimized harnesses to the practitioner or OSS fuzz or whoever, and then just start fuzzing them at massive scale. And so over time, we actually can converge on valid, broadly covering harnesses in as little as 10 minutes for some of these libraries. And I want to state that this was for our single core implementation of this approach. We've since moved to kind of parallelizing this, so we can actually bring this down even more and more and more. And most importantly, we're not requiring any reference code, no specifications, just purely using the library headers that are right in front of us. And so to evaluate this, we came up with a prototype that we call OG Harn, Oracle Guided Harnessing, which as of this, as of right now, that we currently support C libraries, but we have some ongoing work on extending this to C++ and other languages. I'll talk about some work on our efforts to bring this to Python shortly. And we took 20 real-world APIs, 16 that had existing manually written, developer-written harnesses, and then 4 without, to also test the case of like, how do we generate harnesses for ones that have not been fuzzed thoroughly before. And so we conducted the usual campaigns of a bunch of 24-hour trials per harness, looking at coverage, correctness, and then of course bug finding, comparing to the sort of mutational, sort of not guardrail driven approach Hopper, and then of course whatever manual harnesses exist for those libraries, which was 33 in total across all 20 of these libraries. Is there a question in chat here? How do you identify if a function is initialization, auxiliary, or processing, et cetera? Do you just try to any combo of functions to see what sticks? So we have some lightweight heuristics. We did a lot of surveying of all these C libraries that are actively being fuzzed. And what we saw, for example, is that most initialization routines, I think it was like 90-something%, had init as a keyword in the name of that function, right? Obviously, there are cases where these heuristics might be violated, but we've seen that overall, I mean, they have pretty good generality. And so we actually allowed users to then maybe make tweaks to our approach to say, no, this is actually the initialization naming for this library, kind of go away from your default sort of heuristics. If that answers your question. But yeah, it's all just kind of basic heuristics of like looking at what arguments they take. In the case of like data entry points, we look for functions that take in a buffer or a file name or a file descriptor. and yeah, just begin stitching together things and then seeing what sticks over time as this functionality is correctly called and deeper behavior is exercised. So our first, kind of question here was like, well, how correct are our harnesses, right? Obviously, we have some guardrails. Does that actually help us in generating valid harnesses that, I avoid false positive crashes? And so unsurprisingly, I mean, all of the, manually written harnesses for these libraries, again, they were meticulously written by the developers or, practitioners, experts, whatever. And, they don't see any false positive crashes, right? Every single bug that we saw reported, through through fuzzing these harnesses, was confirmed by developers, right? Hopper, on the other hand, different story, right? So again, kind of underscoring the lack of its semantic guardrails is like all these different errors that we saw. For example, blatant kind of misuse of API functions, invalid parameters set up to different distinct API calls, or in other cases like, double deallocations, all kinds of other things, missing initialization functions, all that stuff. And so most of the bugs that we reported from fuzzing with Hopper were rejected by the library developers, right? Let's see. Okay. And we conducted an initial evaluation of our correctness. I mean, most of our fuzzing campaigns are just done on the top 10 sort of highest coverage harnesses that we then, retrieve from our minimized set per library, just in the interest of trying to not blow up our resource demand. But across fuzzing all those top 10 harnesses per library, we found 41 true positive bugs, and no bugs that we reported were rejected by developers, right? When we eventually scaled this up to all of the harnesses, like if it was several hundred per library, we didn't see any other signs of false positives. And we also found a new bug along the way in libgeos. And so, our kind of takeaway here was that by using these guardrails of compilation, execution, and increases in code coverage, we actually can converge on correct, thorough harnesses that uphold the sort of unwritten semantics of the APIs that we're trying to fuzz. And in looking at the code coverage of our harnesses versus our competitors, so unsurprisingly, we cover a whole lot more functions than the manually written harnesses for most of these libraries. About a 14% increase in total library-wide coverage, but we also covered a lot more code that these harnesses do not. So about 364%, distinct code coverage that the manually written harnesses just completely miss. Now, comparing to Hopper, which of course doesn't have any sort of guardrails on how it tries to stitch together API call sequences, it does end up covering more code than us, but at the steep expense of correctness, right? And so because they're not performing any validation, they can actually force execute functions in incorrect states, which kind of gives them the illusion of more code coverage, despite a lot of that execution just being semantically incorrect. And then, of course, looking at our total and uniquely found bugs. And so manually written harnesses, they found 11 total, 4 of which were found only by manually written harnesses. Hopper found a little bit less, with 8 total bugs found exclusively by Hopper. And then we found 41 total bugs, no false positives, 32 of which were found exclusively through our approach, with 40 of them patched after our reporting. And so our takeaway here is, clearly by adding in these oracles and kind of mimicking how developers write harnesses by hand, we actually can, find a lot more bugs than existing approaches at harnessing. And so overall, why do we want oracle guided harnessing, right? So prior approaches for generating fuzzing harnesses are kind of constrained by this need for reference code examples of the library under test, or specifications that you have to write by hand. This is a huge bottleneck. Obviously, it's not going to work. Or in the case, where we're doing away with these restrictions, we encounter a lot of false positive crashes. Our approach, we only require header files. We structure our harnessing based on common case patterns that we observe across, many libraries. And then by adding in these oracles that validate each single step of mutation, we can converge on valid harnesses that find more bugs without false positive crashes, and also increase coverage of these libraries that we want to test. And so, as I mentioned, this was published at ICSE in 2025. And so we have our prototype that's been open sourced. We're making lots of additions behind the scenes. There have been some more features added since our paper's acceptance, but I encourage you to check it out at the following link. All right, so I'll continue talking about our efforts to extend this approach to different library ecosystems, of which we've currently been focusing on Python over the last year. So interestingly enough, Python is actually the second most fuzz library on Google's OSS Fuzz. There's about 600,000 unique Python libraries in existence today. And one of the interesting features of Python is that it can actually invoke native backend code, right? So if you have like some front-end code for these libraries that have Python components, they actually oftentimes use C, C++ in the backend for more speed. But at the consequence of bringing in many of the same types of critical bugs that we see across C, C++ code bases as well. So Python has a lot of importance here, not just because it's so popular, but because from a security standpoint, there's a lot of potential damage in sort of the underlying components of these libraries. Now, funny enough, right, you'd think that with Python being the second largest ecosystem of libraries that's being fuzzed today, you think there is a proportional amount of attention devoted to harnessing Python libraries. And actually, there really isn't. These are some of the most recent papers on harnessing. They're all focusing on C, C++. And so our kind of question here in looking at this landscape of research is like, well, then why is Python harnessing still so immature? What is preventing these approaches from directly being ported to the Python ecosystem? And so in looking at this deeper, we saw kind of three central asymmetries that are making these existing C, C++ style harnessing approaches incompatible with Python, right? The first is, as I mentioned, a lot of Python code spans both pure Python and this kind of hybrid, design where there's native C, C++ called in the underlying backend components, right? And this is really problematic, right? If you're designing a harnessing approach, you now need to juggle this challenge of I have to analyze both the Python code and also whatever other code is in the library that's not directly Python. And I have to kind of homogenize this representation somehow. And if you fail to do that, you actually miss key semantics like native C, C++ defined exception types and all kinds of other things in between. The other interesting thing with Python is that there are sort of non-standardized oracles for what counts as a bug, right? So in one library, right, a type error might indeed indicate a unintentional bug, whereas in others, they might be catching type errors and saying, well, if we do find these are not true positive bugs, right? These are meant to be just rejected because they are expected behavior, right? Given some sort of, malformed test cases. And so this makes it really difficult to come up with kind of standardized oracles for bugs. In C, C++, everything that is a seg fault is determined to be a crash, right? Every time we see a seg fault or maybe some other kind of, assertion violation, whatever, we say this is probably a sign that something interesting has happened. Let's, dig deeper in here and then, report this bug. Not the case for Python, right? Many harnesses for Python actually, do a lot of work to filter out exceptions that the developer simply does not care about. And then lastly, Python is dynamically typed. Sometimes developers will provide type annotations. In many cases, they don't, right? And so without this information in front of you, it's really difficult to stitch together the data flows, right? Arguments to functions, return values to other arguments, all these things that are needed to piece together these larger, deeper API call sequences. And so in the case of C, right, all that type information is available right there. And so you can't simply take those approaches and directly port them to Python. And so overall, what we see is a lot of these harnessing approaches that are being developed today for C, C++ are relying on these sort of rigid, standard semantic guardrails about how they try to harness the library under test. And so our goal here is to take some of these principles, but then refine them, right, on the fly as we learn more about the semantics of the library that we're trying to test. And so our kind of central design here was to augment our existing approach for C with some additional Python-specific handling, right? Mainly supplementing our existing static analysis, which we've actually made to be cross-language to capture both Python-defined exceptions and code and artifacts, as well as things defined on the C++ side, with this additional dynamic sort of refinement of type and exception information that we would obtain as we call more of the library under test. And so our first, step here, kind of like we did for the C side, begins with analyzing as much of the library code as we can. We wrote a lot of components to, again, manage this cross-language boundary and pool together as much information as we can get. From there, kind of like how we do this for C, we begin stitching together different API call sequences, resolving different arguments for each single API function. But then along the way, learning, what kind of exceptions may be intentionally caught by the API, as well as, doing inspection and seeing what kind of type information we can obtain, from seeing what this function returns or doing other, kind of analysis along the way there. And then lastly, again, we would filter out everything based on our oracles. In the case of Python, we would look for there not being any obvious signs that the harness is crashing or returning exceptions on kind of standard test cases. And if all works and we're getting new coverage, then we would then minimize our corpus, but also begin adding some kind of harness-specific library-tailored exception filtering, trying to mimic the kind of exception filtering that takes place in many manually written harnesses for Python libraries. And then you'd pass this off to whatever Python fuzzer you would use. In the case of most Python fuzzing today, we're simply just using the Atheros fuzzer built by Google. And so with only a minimal additional tailoring, our approach can be pretty easily extended to harnessing both pure and hybrid Python libraries. And so we evaluated our approach. We implemented this as a prototype that we call Snake Charmer across a ton of different libraries, 13 of which had kind of native C++ code in the back end, 8 of which were only written in Python, 15 without any explicit developer added type annotations, as well as some libraries that come shipped with CPython's core, as well as 18 that are third-party libraries popular among the Python user ecosystem. And so, as I mentioned, there's not a lot of space. There's not a lot of work being done in the Python harnessing space. There really only is one technique that we know of called PyRT fuzz. And so we evaluated against that. It's kind of like Hopper, but has a bit more Python-specific handling. We also took whatever OSS fuzz harnesses we could get for these different libraries, which is 42 in total. But we also compared to Google's large language model-driven harnessing approach called OSS fuzz gen. And so overall, our first step was, of course, looking at correctness. We compared the type information that our approach recovers dynamically to the ground truth type annotations that the libraries that have type annotations gave us, but also looking at the exception filtering that is embedded in their manually written harnesses to try to see, like, are we filtering out the same exceptions that developers would, based on what we're seeing in those harnesses that are actively being fuzzed. And so comparing to the ground truth type information, we had about 95% accuracy. So there are some cases where there's room for improvement, but overall, we can actually recover a lot of this information on the fly. Excuse me. And then in looking at our exception filtering accuracy, we hit about 97% accuracy with respect to our ground truth manual harnesses. So overall, by adding in this kind of on-the-fly refinement, we can actually kind of do pretty good in handling these Python-specific hurdles that impede direct porting of kind of C++ style approaches. Again, looking at code coverage, we look not just at library-wide code coverage, but also coverage of the native C++ backend components where, where they were relevant for libraries that actually have them. And then also looking at distinct code coverage. This is what we mean by unique code coverage here. And so unsurprisingly, we're covering a whole lot more than manually written harnesses, a good deal more than the existing state-of-the-art Python harnessing approach called PyRT fuzz. And then against Google's own widely deployed large language model driven approach, we're beating that by a good margin as well. So by taking the principles of Oracle guided harnessing with additional sort of lightweight Python specific tailoring, we can really extend the state of the art in Python fuzzing harnessing. And then lastly, everyone's favorite experiment, looking for new bugs found. Developer harnesses found 8 total bugs of which 3 of them were exclusively found by developer-written harnesses. Both PyRT Fuzz and Google's OSS Fuzz Gen found no bugs whatsoever, and our approach revealed 24 in total, of which 19 were only found by our approach. So overall, we are finding quite a few more bugs. 17 were since confirmed, 13 were patched after reporting. Interestingly, we also found a 17-year-old bug lurking in CPython's email module. So pretty fun results there. So in looking at why this is kind of an awesome approach, existing approaches for harnessing C++ are restricted. Excuse me, C and C++ are restricted, exclusively by kind of hard-coded, inflexible guardrails about what they deem to be a bug, how they piece together API functionality, all these different things. And this leaves them kind of, inflexible to supporting Python, which has much more nuance from one library to another about what constitutes a bug, or in the cases of type information, how do we then piece together correct API sequences and whatnot. So our approach, we take the principles of our Oracle guided harnessing technique, add in some additional dynamic refinement that we perform as we exercise more of the library under test. And through this additional kind of hybridization of static and dynamic analysis, we can actually support Python with very little additional tailoring. And so this is still kind of under submission right now. I promise we'll open source it once we get there. But for now, it's still pending reviewer acceptance. And so I know I'm kind of short on time. I'll talk briefly about our existing work. We have some ongoing efforts with Google right now and kind of looking toward hybridizing harness generation. And so right now, a lot of the work on automatic harnessing is focusing on using large language models, right? These are a pretty, intuitive thing to use. They know a lot of code. They've been trained on, all these different code bases, all these different, reference examples of a library being tested and whatnot, right? But what we see is that, they have pretty distinct strengths and weaknesses with respect to mutational-based harnessing approaches like our Oracle-guided harnessing. And so this is a kind of case study of one of the bugs that our approach found in HDF5. As you see here, we first pieced together the entry point routines to actually pass fuzzer generated data into the library under test by calling this h5f open function with these mutationally determined flags. And then from there, we feed that API returned object to this function h5g get info, which with a specific test case causes a crash. And so what we saw in performing our experiments was a lot of bugs were actually found not necessarily in these initial kind of entry point routines, but they were found in calling these deeper API call sequences beyond, right, where you're feeding API return data to this function and that function and just stitching together more and more kind of deeper calls from there. Now, OSS Fuzz Gen, this is kind of the state-of-the-art approach used by Google right now that's using LLMs to piece together harnesses. They actually can do pretty good at recovering these entry point routines to inject fuzzer generated data, right? So here, they correctly call HDF5's h5f open routine with all the, kind of constituent arguments that it need to be there for it to be exercised correctly. But when you start saying, well, now try to call the same function that we were able to successfully harness to find a bug, they actually completely drop the ball, right? If you actually try to run this, it's not going to take in any fuzzer generated data. It's not going to be usable, right? It's just incorrect. And so in looking at this, we're seeing that large language models are pretty good at setting up this initial state for injecting fuzzer generated data, right? Which could include calling initialization routines, entry points, any other kind of library specific setup. They're great at that, but they really struggle at harnessing the deeper functionality that is exposed through API to API call sequences, right? And so this is kind of grounds for a more hybrid approach. Now, conversely, like our approach actually can do pretty good at covering these deeper API to API sequences. We actually looked at the bugs that Google has disclosed were found by OSS Fuzz Gen versus the bugs that we reported. And we found a higher proportion of bugs that were caused through these API to API sequences, right, compared to Google. And so this kind of further underscores that, they're really good at scratching the surface, but when it gets to exercising deeper code, that's where they struggle. Now, our approach, right, as you can probably imagine, relies on a lot of heuristics, and this makes it difficult to piece together very complex initialization entry point routines, right, for some libraries. So for example, libtiff has kind of a sort of non-standard way of piecing together data to call some functions. Our approach just could not figure that out whatsoever, and this leads to missed coverage, false positive crashes, and all kinds of other, derailment there. And so our motivation in taking on this project was, how can we combine the strengths of large language models that piecing together these kind of precise routines to begin exercising things in the library with our approach of mutationally trying different call sequences at a pretty high speed. And so our idea here is to kind of, again, leveraging like some of the insights from hybrid fuzzing, where you have kind of a generic, fast, dumb mutation approach with a slower, more precise, mutation thing. Typically, it's like concolic execution or symbolic execution, something like that. But anyway, there's this trade-off of something that's slow but precise with something that's fast but kind of hasty, right? And so if you can actually manage this trade-off, right, and delegate specific tasks to one over the other, you actually can cover a whole lot more code than you would by relying on either of those techniques in isolation. And so kind of like, our initial approach, we would begin by extracting as much information as we can from the library under test, and then begin trying to synthesize the initial entry point routines to feed the fuzzer generated data to the library under test, and then delegating, the kind of exploration of API to API sequences to an approach like Oracle guided harnessing, which can quickly kind of explore those and throw out invalid candidates. And then in the case where more refinement is needed, we can default back to the slower yet more precise LLM to attempt to kind of figure out or resolve broken kind of dependencies or whatnot. And so our overall approach here is to combine the sort of precision of slow, costly LLMs with the speed of mutation-driven harnessing like Oracle-guided harnessing, where we would delegate the initial library setup and fuzzer data injection to the large language model, and then quickly mutate and explore API to API sequences via our approach, and then fall back to LLM sparingly in the case of more precise resolution being needed for specific arguments or specific API to API data flows or whatnot. So our envisioned outcome here, this is still a work in progress, we've just kind of begun working with Google on this, is to expand library harnessing and bug discovery at only a fraction of the cost of what they currently spend on using LLMs for this in its entirety. So with that, I'm happy to take any questions. Thank you so much. And I encourage you to check out our prototype. All of the bugs that were found across all the work I've talked about are listed on this link here. And yeah, happy to answer any questions about our work.
Great, thank you. I'm going to grab this presentation back real quick here. Okay, I'm going to go ahead and just talk about a few things and let people type in questions if they want to keep asking questions. So first off, thank you again for presenting. A few community updates. We have the NSF Cybersecurity Summit coming up October 20th through 24th. Registration is open and our hotel block is available. There's an extension into tomorrow for one of the hotel locations and one on Friday, I believe. So if you haven't booked your hotel, please do that. You can find more information about the summit at trustedci.org/summit. And then, as always, to view presentations, join the announcements mailing list, or submit requests to present, visit us at trustedci.org/webinars. I don't see any questions yet, so I'm just going to ask the audience to raise your hand or type in a question if you want to ask Stefan while we have him available.
I don't actually see any audience members.
Yeah, that's okay. That's okay. Well, your email is up here, and so I can distribute that after the presentation. And with that, I want to thank you again, Stefan, for presenting and everyone here in the audience for watching. Hope you all have a good day.
All right. Thank you so much. It's been a pleasure.
Thank you. When I hit end, you'll be kicked out. So don't don't feel like I'm being rude. That's just how the webinars work.
No worries. Thank you.
All right. Bye-bye.
Bye.